Hey, I'm Della, and this is my first of, hopefully many, video essays in which I explain the design process behind my projects. I've been programming with Unity as both a hobby and means of better learning object-oriented programming since I was 13 way back in 2023. And even beforehand, I was learning programming online from the age of 11 back in 2020. This time around, I'll be explaining my Unity Helpers library, something I designed and programmed over the span of a month, give or take. So sit back, relax, grab a cup of tea, and let me walk you through it. The Unity Helpers library was created with the sole intent of making programming in Unity cleaner and more efficient. Most of the functions within the library perform operations that would otherwise take up several lines worth of code, simultaneously making a script larger and harder to read. With the Helpers library, several lines worth of code, for example, a typewriting text operation, can be condensed from 290 plus lines into a single clear function call. It's not that we're completely removing these lines, but we are instead delegating them into a consistent multi-use function. And if it could be done for something like text, why not for other components? That inspired me, and I started to program helpers for some of the more frequently used Unity components and features, creating a library of 11 classes and 80 plus documented functions. Now with that out of the way, let's move on to the more interesting part. The helpers are a collection of public static classes, each one dedicated entirely to their own component. As a recording, there are currently 11, and are dedicated to the following Unity Engine components, with others being dedicated to non-component features, such as scene management. On a side note, these scripts are also entirely decoupled from all but the queuing system. Inside these classes are functions that can be publicly called from any other class. I have separated these functions into 4 types, based on matching behavioral patterns and similar programming structure. Component effect types affect a target component with an external force, found primarily in the rigid body helpers. Functions like push and accelerate, which affect a rigid body using the add force method, count as component effect types. They're usually too touchy to use queuing or delegation and will always be executed immediately upon being called. Value change types change or modify a value within a target component. They are found in the majority of helpers. Functions like setMask and recolor, which generally use interpolation to smooth between two values, count as value change types. These functions will always use queuing and delegate the execution code to a private coroutine within the class. Setting change types change or modify a setting within a target component, found primarily in rigid body helpers. Functions like constrain, which modifies the constraints on a rigid body, count as setting change types. They don't use queuing and don't delegate to coroutines and will always be executed immediately upon calling. And lastly, the value return types return a value from within a target component, found in the majority of helpers. Functions like getColor and getIntensity count as value return types. They don't use queuing and don't delegate to coroutines, and they will always be executed immediately upon calling. When a function is called, the execution varies based on the type. Component effect, setting change, and value return types all immediately execute the code within their function, no delay. Value change types call an internal function, which we've called checkQ, to determine whether there is currently a coroutine running on the same object affecting the same component value. If so, then the coroutine is moved into a queue to be executed later. If not, it's allowed to run and is tracked from start to finish by the queuing helper. What happens within the coroutine depends on the operation, but as an example, most numerical value changes follow a similar looping pattern. When the function ends, the queuing helper is notified. The currently running coroutine stops being tracked, and any coroutines within matching queues are put in its place, repeating until all queues are emptied. Now's a good time to dive into the queuing system itself. I've mentioned it several times, yet haven't fully explained it. The queuing helper is a single public static class that is entirely decoupled from all other scripts. It is entirely dedicated to queuing coroutines and preventing conflicts, and its design makes it a versatile and reusable feature of the static helpers. Within the script are 2 vital dictionaries that we'll be mentioning a lot, so try to remember them. Firstly, there is the current coroutines dictionary. The key is a game object, specifically the game object to which the component that the coroutine is affecting is assigned. The value is a secondary internal dictionary, one that uses a string as a key, a string set to the name of the component value that the coroutine is affecting. The value of this internal dictionary is a coroutine, the one that we are running. Secondly, there is the queue dictionary. Similar to current coroutines, the key is a game object to which the component being affected by the coroutine is assigned. The value is a secondary internal dictionary, one that uses a string as a key, a string set to the name of the value the coroutine is affecting. The value of this internal dictionary is a list of coroutines, the queue for the specific object and value. Like I said before, we'll reference these two quite a bit, so try to remember them. Within the queuing helper are 5 vital functions that handle the entire operation, from allowing coroutines to run, to adding them to queues, to pulling items from said queue and running them. Allow me to walk you through them. Starting with CanRun coroutine. CanRun coroutine is a public call that uses checkObjectKey and checkIDKey, two functions we will explain momentarily, to search current coroutines for a gameObjectKey and a string key matching the gameObject and string variables passed through the function call. If both matching keys are found, then a coroutine of the same type is already running. The new coroutine that is passed through the function call is then passed through addQueue and is not yet permitted to run. If only a matching gameObjectKey is found, then the function creates a new string key using the passString variable and adds it to the internal dictionary within current coroutines, assigning the pass coroutine as a value. The coroutine is then allowed to run. If neither are found, the function creates a new gameObject key from the passed gameObject variable and adds it to current coroutines. It then makes a string key from the passString variable and adds that to the internal dictionary within the current coroutines, assigning the passed coroutine as a value to said dictionary. The coroutine is then allowed to run. Moving on, we have checkObjectKey, a private internal helper function that checks current coroutines for a gameObject key matching the passed gameObject variable. It returns a Boolean value and has an out variable sending out the internal dictionary assigned as a value to the gameObject key. Similarly, we have checkIDKey, a private internal helper function that checks current coroutines for a string key value matching a passed string variable. It returns a Boolean value. And now we have addQueue, a private internal helper function that assigns a coroutine to the queue dictionary. If the queue has a gameObject key and an internal string key matching the passed gameObject and string variables, the passed coroutine is added to the list assigned as the value of the internal string key within the internal dictionary. If the queue has only a matching gameObject key, a new string key is created and assigned to the gameObject key's internal dictionary with a new list containing the coroutine assigned as a value. And of course, if neither keys are found, a new gameObject key is created within the queue, as is a new internal dictionary, in which a new string key is created and a new list containing the coroutine is assigned as a value. And last but not least, finish coroutine. A public function called within a coroutine when it is complete. It clears the gameObject and string keys from current coroutines and searches a queue for a matching gameObject and string key. If a list containing a coroutine is found, then it is executed and added to current coroutines, and so the cycle repeats until the list within the queue is empty, in which it is cleared and the function ends. Now, whenever a queuable function is called, it must initially pass a check by calling a private function within the helper class called checkQueue. This function accesses the queuing helper and calls CanRun coroutine, passing in the affected gameObject, ID string, which is preset and passed automatically to checkQueue from within the function call, and the coroutine is attempting to run, including all of the variable passes. If the coroutine can be run, i.e. there is no matching item in current coroutine's dictionary, then it is allowed to execute without issue and is assigned to current coroutines. If the coroutine cannot be run, i.e. there is a matching item in current coroutines, then it is passed through addQ, where it searches for a matching game object and string key containing a list, creating a new one if necessary, and adding the coroutine. Now I'm going to recap everything so far and wrap this thing up, because it can seem pretty confusing. The Unity Helpers library is a collection of static classes and function calls used to perform operations on commonly used Unity components and features. When a function is called, depending on the type, the execution varies. Component effect, setting change, and value return types all immediately execute the code within their callable function, no delay. Value change types call an internal function to determine whether there is currently a coroutine running on the same object affecting the same component value. This function calls a public function from within the queuing helper, which searches a dictionary containing all the running coroutines using game objects and strings as keys to separate the types of coroutine that could conflict with one another running on the same component object. If there is a coroutine found on a matching string as the one passed through, then the new coroutine is not allowed to run and is instead added to a secondary dictionary that serves as a queue. When a coroutine finishes running, it calls another public function from the queuing helper, which removes the item of matching past string and game object key from the current coroutines. It then searches a queue dictionary for a list found under a matching game object and string key. If that list contains a coroutine, that coroutine is then run and added to current coroutines. This cycle repeats until the list is empty, after which it is subsequently removed from the nested dictionary. And this of course happens every time a queuable function is called. With the libraries complete and eventually going to be put on itch.io and perhaps even GitHub as well, the question remains, what next? I am very proud of what I have achieved thus far, but there are always higher mountains to climb as the system is far from perfect. For example, when a function is called and the coroutine added to a queue, there is no way to remove it. You just need to wait it out, an inconvenience that I would be keen to design and program a fix for. Then there is the obvious approach of adding support for more components and more operations for existing components. And of course, there will be unforeseen errors I may yet have discovered within both the code and the design itself, errors to be fixed and to learn from. But overall, I'm pleased with the outcome of this endeavour, and I'm glad that I have had the opportunity to create it. I hope that many others may find it useful. Della out.